begin by acknowledging the traditional owners of the land on which we gather today and the many lands on which we undertake our work. For us here in the Geoscience Australia building, that's the Ngunnawal and Ngambri people. We recognise their continued connection to these lands, water and culture, and pay our respects to their elders past and present. So a few thank yous before we get started. Thank you for our corporate members who, without this, we wouldn't exist and be able to do all these talks and everything else that we do. I won't go through them all here, you can see though. Thank you to our branch sponsors who also put in money in their respective states and territories. I'd also like to thank Geoscience Australia, whose building we are in at the moment. We're fortunate enough that they allow us to use their facilities, their work, all their electronics, and spend some time doing this as part of our job. A few housekeeping etiquette notes for those, and I can see a couple of questions already, but if you have a question, okay, we can still only see the first slide. Hold on for one moment, sorry about this, folks. Now I'm going to assume that that didn't work. If you can, someone in the chat tell me that we're only on the first slide again. Oh, perfect, thank you. I won't go through, I'll quickly go through all our corporate members. They're the same as we see all the time. And our branch members, and again, Geoscience Australia. There is for questions, we have a question and answer bar. We'll answer questions at the end of the talk, but please put them in as you think of them. And a few benefits of being a member. I will not go through all of these, but you get access to journals. You get reduced entry fees to conferences and technical events at your state or territory and other social events, and you get linked into a professional network where you can get a lot of help or experience or just talk to people as you need. And if you want to keep in touch, if you didn't find this event via this email, via the ASEG, please register and you can get notified of all events. So we are very fortunate to have Francesco talk to us today. He has been in Australia for a short time, but has gained a lot of experience and provided a lot of information and knowledge with our AEM specialists. He comes to us from Italy, where he learned his Masters and PhD. But as we're running out of time, well, running behind time, I might just hand straight over to Francesco and let him talk, because he's an interesting person.
Okay, hello everyone, I am Francesco. Thanks Phil for the introduction. I'm from University of Milan. Today I will show you some results and some insights about the induced polarization effects in electromagnetic data. Many of you have already the answer to this question, but I think it is a little provocation and it needs some explanation. So because the thing was to ask ourselves, is extract industrialization effects from electromagnetic data is an opportunity or a completely waste of time, basically. So here's the outline of the presentation. I will show you briefly the idea of extracting IP from Airborne EM and how physically these induced polarization effects can affect electromagnetic data. And then I will present you two main research fields that we are working on with our research group, that are one, regarding the fixed wing systems. We asked if fixed wing systems were able to record induced polarization effects, and if is it possible to model induced polarization effects from fixed wing data. And then I will show you a real case study for mineral exploration about airborne and ground induced polarization integration for detection of ore bodies. Okay, quickly, the idea is pretty simple. And we would like to understand if induced polarization detected by airborne electromagnetic measurement or ground electromagnetic measurement can contribute in enhancing the geophysical exploration capabilities. Now, the state of the art regarding the induced polarization methodologies for the exploration are uniquely or mostly related to galvanic induced polarization survey, so the classic methodology on the ground, because it has given a lot of successful target detection in the history, and it is full of successes, but it is nowadays recognized, and it is known that induced polarization effects can be detected also by inductive measurements. So it is possible to record these effects also from inductive measurements, but it is necessary to understand if it is useful to model these and to use them in exploration. The issues are many and are mostly related to relationships between the ground and inductive induced polarization effects, and between the geology and inductive induced polarization that is measured with inductive measurements. But also at the same time, modeling extracting induced polarization information from electromagnetic data is quite difficult, is highly time expensive, and not suited to automation. And at the same time, it is really suited to equivalencies during the modeling of this data. At the same time, these efforts can worth in terms of decreasing and lowering the economical and human risk, because it would be useful and fantastic to design around this survey based on Airborne EM large-scale survey, given that typically the electromagnetic measurements are way faster and quicker respect to the ground galvanic measurements. And also, it would be of interest to understand if the airborne EP or the inductive EP in general measurement can increase the geophysical sensitivity to the ore body detections. So, but how inductive induced polarization works? Physically, it is known that when we measure electromagnetic data over a capacitive Hall space, this Hall space will behave like a capacitor. So it is able to complete a full charge in the discharging cycle and producing an energetic current into the ground. That is the polarization current. This current will be summed to the purely electromagnetic current during the charging phase of the ground, and will be subtracted to the purely inductive current during the discharging phase of the ground. So what happens is summarized in two typical signatures in the recorded data that are a typical a typical pull-up of the recorded data at early times that is given by the sum of the two contributions in terms of current into the ground, and the pull-down of the recorded signal at late times that is given by the subtraction of the P currents to the purely EM currents. If the induced polarization current that is developed in the ground is stronger enough and more strong, the purely EM current, it will be possible to measure negative voltages. So these negative voltages are considered like a typical signature of induced polarization effect, but it is true only for concentric loop systems, and because for offset systems, these negatives are not uniquely related to induced polarization effects. when recorded in the data. It is possible to model these effects using a dispersive resistivity model, such as the call one. It parameterizes the investigated half space with 4 parameters that are the resistivity, chargeability, the time constant, and the frequency dependence parameter. So, but what about real data? Here we have an example of a line acquired by an helicopter-borne platform, so an Airborne EM data. In red are displayed the negative voltages that has been recorded over that line, and we did 2 experiments. So we tried to model this line with a non-dispersive resistivity and with a dispersive resistivity, and we knew that this line was affected by induced polarization effects because of evident negative voltages. This is what we get. If we model this kind of data with a non-dispersive resistivity, we obtain a really high inversion misfit, visible in the bottom left figure and represented by the continuous black line, but most importantly, a completely different structure as visible between the comparison between the non-dispersive and dispersive resistivity. So we can miss important information for the description of the investigated underground, but also it will be possible to measure and to model important features. And another parameter, as told you before, that is the chargeability, that could give important information for the exploration, for the description of the ground. It is important to understand at what is related this chargeability that we measure from the Airborne EM systems or with the inductive systems. From bibliography, so until a few years ago, the chargeability we measured is thought to be related to not really interesting geological features. So such as fine-grained materials, alteration, so non-economic materials, that in terms of parameters, these are described by high chargeabilities and low time constants. We will try with these examples to understand if happens something also for low time constants and higher time constants and low chargeabilities that would mean the entire parametrical range with which we discretize the half space and that can contain also more geological information, more interesting. So I'll start again now with the fixed wing research. So we asked ourselves if fixed wing systems were able to detect induced polarization effects. This is not an obvious question because airborne EP is typically associated with airborne helicopter-borne platforms, so with concentric loop platforms such as VTEM, SkyTEM, and Excite, and many others. But what about fixed wings? It is complex because modeling airborne EP from fixed wing data, for this data, it is not easy to recognize induced polarization effects because, again, there is not a unique relationship between negatives and IP given by the offset between the transmitter loop and the receiver loop. And also, these systems have a really high, a big footprint, so that means a lower shallow sensitivity. So, at what a lower sensitivity to the chargeable feature that we can expect in the underground. But the effort can worth, given also because maybe you well know that it is possible to acquire tons of line kilometers in a small time with this kind of systems, and it is possible to acquire continental scale projects like the ASEG. So modeling airborne IP from fixed wing systems would mean to find a treasure, but also to find new nightmares if it is true in terms of complexities of modeling. So we started with synthetic study. We try to understand again if fixed wing systems are sensitive to induced polarization effects. We basically did a comparison between a couple of 2 layers model, one capacitive and one purely resistive. These models are described by the capacitive one by the call parameters and the purely resistive by the only resistivity and thickness parameters, and we calculated the forward responses for each of these half spaces using the same resistivity and thicknesses. So with this, we assume that the distortions that we measure in the differences between the two forward responses are attributable to induced polarization effects. And if these are detectable or not will be resumed in the distortions that we can measure. So we will quantify the distortions between the forward responses, and we represent the distortion because we calculated these comparisons for 1,000 of couples of half spaces. Slowly, I will show you an example. Here we have for a response of a purely resistive half space, represented in blue, while in black is represented the noise level we used. Adding some chargeability to the half space for which we calculated the forward response allows us to calculate another forward response that is like this. This is an IP affected forward response for the same half space with some chargeability. And as you can see, there are some distortions in the data, of course, that are the typical one that I was describing before. So negatives at late times, fast decays, and pull up at early times. How we quantify these distortions with a simple absolute percentage difference that is calculated gate per gate, and then we get the mean of these absolute percentage difference. But we decided to calculate these differences not all for all the gates, but only for the gates of Dauti noise level. So we decided to use to quantify the IP distortions that are measurable. We calculated these distortion for 1,000 of couples of transients of forward responses, and we displayed in a two-dimensional plot like that. That is like this, where we have a distortion in the color scale that goes from 1 to 100% of distortion. We make two parameters on the axis. Here, for instance, we have the chargeability, and here we have resistivity. Here we have the chargeability we use for each forward responses span from 100 to 1,000, while the resistivity is from 1 to 1,000, and we kept fixed to the rest of the parameters in the title. This because it was not easy to display all the distortion for all the parameters that vary in altogether. This is what we observed in this kind of graph. Each point represents the distortion for a couple of transients, one affected by industrialization and one not affected by industrialization. It is visible how the distortions are present in the entire parametrical domain, parametrical range we used, with more intensely for higher chargeabilities and less intense for lower chargeabilities, of course, but are present also for low chargeability values for a central resistivity range. So you can see that the distortions given by IP effects and that are detectable are quite diffuse in an easy two layers model, an easy half space. But it is important to understand what is relevant in terms of distortions, because we have a span of distortion that goes from 1 to 100. So it's important 100% of distortion and 10% or 5%. Well, we have the answer because we typically fit the Airborne ELM data acquired from fixed wing data in a percent that goes from the 3 to the 5%. So everything that is above this 5% of confidence that we have in fittings data can compromise the modeling, basically, because we would fit easily with a purely resistive model a data affected by industrialization effect. And again, it's interesting because even for low values of millivolt volt, we can see significant distortions for fixed wing data. So what about the negatives? Because as told you before, the negatives are related, but not easy to uniquely related for this kind of systems. We have negatives, but not everywhere where the distortion are, let's say. So it is important to see again that we can have induced polarization effects even if we don't detect negatives, as we will see in the real data example that I will show you now. Real data is this one. We have two surveys flown in the same area. A VTEM one represented in green. So an helicopter-borne concentric loop platform, and the geothermal one represented in black. Some lines are overlapping. To give some context, we are in Australia, in the Northern Territories, and the aim of the geothermal target was to estimate the cover thickness. Well, something more about the geothermal. The geothermal system is a fixed wing system with a theoretical receiver position that is 50 meters below the craft and 70 meters behind the craft. This acquisition is quite old, so at that time it was not possible to measure the receiver position, and they estimated the receiver position after the acquisition. So this estimation of the receiver position was based on the data. So it is not, if the data are affected by distortions, it was not easy to obtain the receiver position during the estimation process. So we use the theoretical bird position for our modeling, and also again for some specific to put more context, that you can see that this system is pretty different from the Witten's one in terms of dipole moment. It has a really big dipole moment if compared to the Witten dipole moment. These differences in geometry and in dipole moment are visible in the data that they measure. As you can see at the top, we have the Witten one, where it's interesting that are displayed also some negatives in a portion of the data stripe that are not recorded for the geothermal overlap data that are described below. We have some fast decays for the component and correspondence of the negatives of the Witten, but we don't have negatives, and maybe neither evidences of induced polarization effects in the geothermal data. But anyway, we try to model it with a dispersive resistivity model, both of the data set. And this is what we got. At the top of this figure, you can see the resistivity model obtained by the Witten. And at the bottom, you can see the resistivity model obtained by the geothermal. Of course, these two are different because of geometrical differences and dipole differences and all the things that we saw before. The data are different, so the models are different, basically. And are different in terms of resolution, but they can describe the investigated half space more or less in the same way. So in describing conductive domains and more resistive domain with this very similar thicknesses of the first layer, for instance. And for all of the data, we fit the data with a really good misfit that is quite low, below 1. What about the chargeability for these lines? We have this chargeability. It is not really exciting because it is very shallow and mostly related to the first layer, but it has been possible to model this chargeability. Of course, we compare the geothermal chargeability, the fixed wing chargeability with the Witten one, because we well know how to manage the Witten inversions when affected by induced polarization effects. But again, it's encouraging to see that the geothermal chargeability is pretty similar in terms of distribution and magnitude to the Witten one. And again, for another line, also the resistivity models are pretty similar with the given differences. The misfit value is quite low. And again, the chargeability models are pretty similar, both in terms of spatial distribution of the chargeability and in terms of magnitude of the model chargeability. I will show you some slices. This is the geothermal resistivity slice, very shallow at 10-20 meters. And this is an overlapping with the results. Both of them modeled with a dispersive resistivity. And then we go a little bit deeper, 100 meters. This is the geothermal, this is the Witten. The results are really comparable. And again, we did the same for the chargeability, the shallow chargeability, as we saw for the section. And the correspondence is not as good as for the resistivity, but for some lines it's very good, for other lines it's not really good. We explain these results because with the lack of knowledge of the receiver bird position, basically, we can fit with induced polarization an erroneous position of the bird that we because again, we use the theoretical Burr position during the inversion. So it is possible that we fit with like P the lack of knowledge in the geometry of the system. So the first conclusion is this little study, is a synthetic study. We show that induced polarization effects are present in the Airborne EM data acquired with fixed wing system, and that is possible to model this in terms of real data. The chargeability we recovered are comparable with the Vietnam chargeabilities, and again, the good fitting does not rule at 100% the possibility that we fit with geometrical lack of knowledge with induced polarization effect. We are working on some joint inversion between mature systems, considering induced polarization effects, and we will show you at the AEM 2023 conference. Okay, the other case study that I want to show you, this is a proper case study for mineral expression. When we try to integrate the ground, the airborne information to detect mineral targets or to detect mineral chargeable anomalies confirmed with the ground induced polarization. We tried. So as we know, there are differences between the galvanic induced polarization acquisitions and the inductive induced polarization acquisitions in terms of everything: base frequencies, sensitivities, and also time of acquisition. Again, the inductive measurements are way faster than the galvanic one, and we are trying to extract this inductive induced polarization from this inductive measurement and compare them with the galvanic induced polarization measure. So for this case study, we are in Spain, in Southern Europe, in Andalusia, to be precious, and geologically, we are in the Variscan Iberian Pyrite Belt. That is one of the areas in the world with the higher concentration of VMS and disseminated deposits. The typical geophysical approach for the exploration in this area was to use the gravimetry to localize the VMS high density deposits. They then proceed with the MAG to discriminate the VMS with the Felsic rock that hosts the VMS deposit, and then they perform the induced polarization measurements in order to localize disseminates and polymetallic mineralizations. What about the electromagnetic measurements in this area? It was not the common practice to use EM for detect this conductive anomalies, because the host rock of the VMS in that area are black shades. So conductive with conductive, it is not easy to discriminate if not integrated with all the other information that are given by the other geophysical methodologies, such as the gravimetry, the MAG, and induced polarization. So these are our surveys. In black is represented the Airborne EM survey. In red is represented the ground IP survey. Some lines are perfectly overlapping, but both the surveys are good. There is a Airborne EM cover over the ground IP surveys. The ground IP has been acquired after the Airborne EM with a dipole-dipole configuration and with a big electrolytic distance typical from mineral exploration surveys. While the Airborne EM is a classic Airborne EM system with a concentric loop acquired with an helicopter, with a base frequency of 25 Hz and a dipole moment of 300,000 NA. Geologically, the area has two main domains, one in the north that is with some outcrop of volcanic rocks, such as rhyolite, dacite, and andesite. And in the north, we have some cover that covers the bedrock, of course. How did we approach the modeling of these two datasets? We decided to be consistent. So we used the same modeling approach both for the ground and for the Airborne AM EP modeling. So in detail, we used forward modeling with a full voltage decay for the Airborne EM survey, of course, but also for the ground induced polarization survey. So we didn't model the data considering the integral chargeability as it is commonly done. We also modeled the transmitter waveform and receiver transfer function in order to avoid the modeling of artifacts during the inversion process. And of course, we did a 2D forward modeling for the galvanic data and a 1D forward modeling for the inductive data. In terms of inversion, we used for both the methodologies for the ground and for the airborne a maximum phase angle reparameterization of the call. It is like a call model, but instead of using the chargeabilities, we reparameterize the chargeability with the maximum phase between the complex resistivity, the imaginary part of the complex resistivity and the real part of the complex conductivity. And instead of the time constant of the call model, we used another time constant that is called tau phi. This is the frequency at which we reach the maximum phase between the real and imaginary part of the complex resistivity. To model this data, we used our inversion code that is called the inverter. It's an inversion scheme that we are actually developing in our research group in Milan that allows to separate the forward in meshes, the forward mesh and the model mesh. And during the inversion process, we can use multiple forward meshes and multiple model meshes in which we parameterize the model space, basically. So for this case study, we kept fixed in vertically the spectral parameters of the MPA parameterization of the MPA parameterization. So we fixed the C and the tau parameters to let them vary only horizontally. This was done in order to increase the phase or chargeability sensitivity in depth, as demonstrated by Fiandaca and Dietzoli 2 years ago at the AGC conference. So let's go through the results. Here we have a resistivity slice at 80-90 meters. As you can see, there are even here, even if it's a little bit in depth, but there are two domains, more or less, one in the south, more conductive, that is the conductive cover, and in the north there is a more resistive domain given by the outcropping volcanic rocks. It is important to notice that there is a known mineralization that is called La Romanera. It's a massive mineralization of copper, strontium, and zinc at a depth of about 100 meters. As you can see, it's well detected by the Airborne EM and it's conductive. We modeled the chargeability. This is a chargeability slice at 20-30 meters of depth. As you can see, again, there is a good correlation between the shallow chargeability and the cover in the south, and there is less information in the north, even if there are some isolated chargeable bodies, shallow bodies, in the volcanic domain of the investigated survey. Things are more interesting going deeper at a depth of 60, 70 meters, because we can see that there are some isolated bodies mapped with the airborne chargeability, airborne phase for this parameterization. So we decided to focus on this isolated body. One is indicated in the yellow. We decided to start with this isolated chargeable body because it is isolated, of course, and is conductive. It is a little bit in depth, so it is conductive as La Romanera mineralization, and is also close to a gravimetrical hub, so to a dense or a dense domain mapped with the gravimetry. We compared with this airborne IP isolated anomaly with the overlapping ground DCIP line. We modeled the ground overlapping DCIP line, and this is what we got. So it is interesting to see that the airborne IP anomaly that was mapped here on the left, it is confirmed also from the ground DCIP modeling at a depth that is the same as So at 60, 70 meters, as you can see from the right side, from the ground DCAP model. Then we decided to move and to see what happens in the north, where we have other localized anomalies. And we did the same. We compare these localized airborne anomalies with the ground DCAP. And again, there is a good correlation with the ground DCAP models that we recovered with the inversion. It is also interesting in this ground resistivity model to see that there is a kind of trend in the chargeability structure that we get from the that we recovered from the inversion. And it is interesting also to see if compared with the geology, because we are in proximity of a geological discontinuity, a tectonic discontinuity, and the chargeability model follows the trend that is described by the geological mapping in surface. We compared another line of ground IP. Here we have at the top a full section of airborne IP phase model, and compared with the ground phase model in the bottom. As you can see, there is a good comparison again. The resolution is different. Of course, in the ground we have a better resolution of the chargeable bodies, but these bodies are mapped also with the airborne EP. So far so good. Not really, or not everywhere, because of course we are missing some chargeable deep anomalies that we met with the ground, and we were blind to them with the airborne. What about the Romanera non-deposit? We have not been able to map it with the airborne survey, but well with the ground is well localized and well described. So we didn't surrender, and we tried to attempt a joint inversion between the ground and the airborne induced polarization measurement. And this is what happened. At the left, you can see the airborne phase model, and at the right, you can see the ground phase model, and in the bottom, you can see the joint inversion result. So the result is quite encouraging and pretty nice, and you can see that the joint model, the chargeability phase of chargeability that is closer to the ground, of course, because it has more sensitivity, but it's not the same. This means that the airborne phase, the airborne AP gives some contribution in the geophysical sensitivity, in the phase sensitivity during the inversion, the joint inversion process. It is also interesting to see that the misfits are pretty similar, those of the independent inversions and those of the joint inversion. Here an example of another line. Again, the airborne independent, the ground independent is the joint inversion. The joint inversion is a little bit different, again, with respect to the ground inversion, and resolution of the two chargeable anomalies is different in terms of, is different in the joint inversion. The misfits, again, remains the same. What about La Romanera? Now, with the joint inversion, it appears. And it's interesting to see that the data misfit for the Airborne EM model independently, not jointly, decreases if in the joint inversion respect to the Airborne EM independent. So this misfit behavior is, so it is interesting to see that we were not fitting the data with the airborne in the Airborne EM, and we were not imaging the known deposit. And it's also true that the La Romanera deposit helps the inversion process to better fit the Airborne EM data. So there is sensitivity to that. Some other partial conclusions: the consistent modeling of Airborne EM and industrialization and DCAP data makes possible a seamless integration between the two methodologies. For this case study, the airborne IP anomalies in that have been always confirmed from the ground. It is not true, vice versa, the opposite. but it is possible to still improve the modeling procedure and inversion process in order to better understand if the problem is the physics or our procedure in the data treatment. Another important thing is that the joint inversion between the Airborne EM IP and the ground DC IP data is possible with the same model space, with the same time tau value, time constant value, with the same data misfit, and we obtain an improved model. Again, more examples I will show you more examples of joint inversion at the September's conference, and then some general conclusion. We obtain promising results. It is possible to recover and model Airborne EP from fixed wing systems, but also innovative modeling and can lead to sensitivity overlap to chargeable anomalies between ground and Airborne EP, and also an integrated modeling can allow us to map chargeable targets also in depth from the airborne data. The airborne chargeability models can provide, as seen with the joint inversion, in significant information when integrated with other geophysical data. The key successful for IP modeling, for our understanding now, using the same model space and the same inversion algorithm to treat different data, but both in the spectrum of induced polarization methodologies, can lead to interesting results. So, finished, and thanks for your attention.
Okay, do we have any questions from the floor here? Yes, sir.
Thank you, Francesco, and thanks for spending some time here with us. I just wanted, when you showed the forward modeling of the fixed wing in one of your slides, one thing I noticed, and I hope you, after some of the modeling you've done here with us, you're gonna take that slide, because you show a negative response on decay. There is sample by, I think I count 24 windows. So that's one thing. Go further back when you do the forward model for the fixed wing.
Yeah, I have lots of slides. Yeah, of course. Okay, I don't know how to do. 5.
I think we just went too quickly.
I broke the computer.
Yes.
Would you like to repeat the question?
Yeah, maybe just go a little bit further so we can get. This one.
Can you repeat, please?
So this is kind of your evidence to show that there's an IP response measurable on the fixed wing. So, but it doesn't, for me, for instance, there's two things that I think you have probably seen with more precision after at least 2 weeks. The fixed wing has usually two components, the X and the set. So that's just your set component, and I guess I don't know what system that is, because that's what
Yeah, it's a GSM. It's an old system. It's really old data. These are only a forward response examples.
Anyway, the point is what I'm trying to say is maybe we can update that slide with using the two components, because it manifests more the X than the Z, which is okay. And also just we have had some interesting discussions about the noise, right? Because that's just a percentage of,
yeah,
but it's not the real measured noise of anything. So that's kind of quite ambiguous. I think
yeah, it is. So they have to repeat the question, I expect. So basically is how why we didn't model the X component also, and where this noise level came from. So we did also for the X component this work, and we have nice. In this presentation, I put only the Z component, but we did also for the X component, and it is interesting to integrate this work with what we talked to in these 2 weeks, because we can get more insights comparing both the components and not keeping them like isolated, or looking at the Z and looking at the X separately. Regarding the noise level, this noise level, I remember it was given us from the data provider or something. So yeah, we used that one blindly.
Yes, thank you, Francesco. Look, it might be an obvious question, but if I understand clearly from airborne induced polarization, to be able to be detected, it would not only have to be chargeable, but it would also have to be conductive. You can't detect chargeable but apparent resistivity highs from induced IP. Would that be correct?
Repeat the question. The question was is if we can detect chargeable and resistive bodies, basically.
Correct. Yeah.
Yes, we can. It is more easy to detect chargeable and resistive bodies because the purely EM currents, if a body is resistive and chargeable, the purely EM current decays faster, proceed faster downward. So while the purely induced current remains in that layer.
Yeah.
So we can measure stronger induced polarization effects if the half space is resistive. From this figure here, maybe I went fast before, we don't measure IP distortions for the most resistive domain, but because of the noise level we used. So here on for high resistivities, all the signal falls into the noise level that we used, but it's not always the truth. So the signal falls into the noise level we used, and we didn't detect any distortion given by induced polarization. But it's possible, and it is easier to measure induced polarization effects when something is more resistive.
We'll have a look at the. Okay, so Antonio says, I've seen it sometimes the ground IP measurements miss the shallow chargeable layers. Could it be due by the large electrode spacing?
Yes, and also from the geological geometrical configuration of the ground DCIP survey. That is a dipole-dipole, so with a high signal-to-noise ratio and with a high separation between the dipoles, that missing sensitivity and information from the shallow portion of the ground.
And we do have a comment about present. Does joint modeling improve AEM resolution throughout the data set beyond the ground IP?
Okay.
That's right.
Oh, sorry. Improve the resolutions without data set. It will be interesting to jointly model all the lines we acquired to see what happens for the entire Airborne EM IP survey. So our hope is that would be possible if jointly modeled the lines to recover the full chargeability for the entire dataset.
That's a thank you for the talk.
Thank you.
And Andrew, you have a question?
I really like the illustration of if you've got IP bias in your response. That to me is the more dangerous one, because where you've got those changes signed, you can't fit it. Okay. Where you've got bias, that's dangerous because there is such ability. In your inversion, you've got to have like an objective function which is balancing various terms that contribute to this thing. So one of the terms will also be the chargeability. So I was wondering, how do you split between chargeability, the three chargeability terms, time constant, something else? Sorry,
time constant.
And the resistivity terms, the electromagnetic, the inductive resistivity. How do you split the amount of misfit budget that you give between the different parameters of inductive conductivity or resistivity? And
Basically, we.
But the question is, how do you set up where your noise levels are set?
I don't know. Is Ross not bullet here?
No.
No.
In the misfit function, in the objective function,
We calculate the global misfit, so we calculate the global misfit.
For any given misfit, part of it will be due to chargeability, part of it will be due to conductivity. How do you split for any level?
So how do you split any level of misfit between the conductivity and the resistivity?
Chargeability.
Chargeability, sorry.
Magnetic chargeability.
In the joint inversion.
Yes. And the resistivity.
Okay, in the joint inversion.
No, in the normal inversion, because you have two current terms. One is the Ohm's part, and one is the which is the inductive part, and then the other is the ID part. So you have
In terms of currents into the ground. So.
you have the sum of two J's.
Yeah.
So one is the.
And we compute the resistivity, the dispersive resistivity after the computation of the normal resistivity. So, no, maybe the question is not clear.
I think you're not really splitting the data.
Yeah.
I mean, the data is just the data, and it has a misfit. But you're probably more asking, how are the conductivity terms constrained versus how are the chargeability, time constant, IP parameters constrained? You have a different
This is
model regularization function
Yes.
for the 4 different types of parameters.
Yeah. How the question is, how do I regularize the 4 parameters basically? We use with the inversion scheme we used 2 model meshes to put the parameters in. Let's say in a model mesh, I dedicated a model mesh to the spectral parameters, so to the time constant and the C parameter. So with their constraints and their regularization, and another model mesh with another regularization for the phase and the resistance. So we use constraints, different constraints between for each parameter.
So in this line, would it be possible to get the smoothest or the most resistive model, which is not something like that? So that would help you discriminate between something which must require IPE and which will not require it.
Yeah, this is it.
You could vary that regularization parameter. So let's see, well, if I can fit the data without IPE, and where I can. So maybe that'll give you some.
It would be interesting. I think that
Because
could
then
be.
you can have a simpler model versus
Yeah,
more
with a
complicated
more.
model which requires IPE.
It could be a way of reduce equivalencies and uncertainties while we use such an amount of parameters. So
have a regularization thing that says the chargeability should be small.
Right.
yeah, it
Sometimes two of the parameters are
yeah during deterministic inversions, yeah, we used to fix parameters in the for side we decide for how many iterations we fix parameters. Yeah, we manage the parameters for each.
I'm going to pull it here because this is a very interesting conversation, but everyone needs to be up on the platform to actually talk, so anyone here can hear it. So I'm going to say thank you. I will take note of a couple of the issues that came up in the chat. That is my fault. We'll fix those for the next time. I want to thank Francesco for giving a talk. So here's a bottle of wine for you.
Thank you.
And thank you very much.
Thank you.